In this video, I'm going to talk about Bessel's equation. Bessel's equation is defined as follows: x square y double prime plus xy prime plus x square minus alpha square times y is equal to 0. And here alpha is actually a constant. And this constant could be real or it could be complex as well. Now, we will consider a very special case of Bessel's equation where alpha is equal to 0. If you set alpha is equal to 0 in this equation, it becomes x square y double prime plus xy prime plus x square y is equal to 0. This is, by the way, is called Bessel's equation of order 0 when alpha is 0. Now, in order to solve this equation, what we are going to do, we are going to express this equation in this format. Y double prime plus p of x times y prime, okay? Plus q of x times y is equal to 0. And we can convert this equation into this format by dividing both sides of this equation by x square, okay? If I do that, this is what I'm going to get. It's going to be y double prime plus y prime over x plus y is equal to 0. Now, as you can see, there is a singular point here, or there is a singularity at x is equal to 0. Okay? We call it, let's say, x naught. Now, what type of singularity is it? Is it a regular singularity or is it not a regular singularity? If it is a regular singularity, then we can solve this differential equation. However, if it is not a regular singularity, then we can't. Now, how do we test for singularity? What type of singularity, whether it's regular or not? Let's consider x naught is a singular point. That x naught will be a regular singular point if these two conditions are satisfied. So limit x approaches x naught, okay, x minus x naught times this lowercase p of x, which is this, in our particular example, is going to be 1 over x. And limit x approaches x naught, x minus x naught whole square times q of x, which is this. In our case, q of x is going to be just 1. If both of these limits exist, then we call point x naught a regular singular point. And as you can see, it's pretty straightforward. Since x naught is 0, our limit x goes to 0, okay, x times p of x. P of x is 1 over x, as you can see, coefficient of y prime, which gives me 1. And similarly, limit x goes to x naught, or in our case, x goes to 0, is going to be x squared because x naught is 0, right? Times q of x. In our case, q of x is just 1, which is the coefficient of y, okay? And the limit is 0. Both of these limits do exist, right? Therefore, the point in question, x naught equal to 0, is a regular singular point, okay? If it is a regular singular point, okay, then we can find the solution. And solution is going to be of this format. Y of x is equal to x minus x naught raised to the power r, summation n is equal to 0 to infinity, a sub n times x minus x naught whole thing raised to the power n, okay? Here n is a complex number. So let's go ahead and continue with this. Now, if I simplify this by taking into consideration that x naught is 0, okay, then what's going to happen is this. It's going to come down to y of x is equal to x to the power r times summation n is equal to 0 to infinity a sub n x to the power n. Now this x to the power r, I could bring it in here inside and multiply it with x to the power n. That's going to give me x to the power r plus n. and it's gonna end up becoming summation n is equal to 0 to infinity a sub n x to the power r plus n. So this is an expression you want to keep in mind, okay? That's your y. Now we are making the assumption that this y is a solution to this differential equation right here. So what we do, we take the first derivative of y, we take the second derivative of y, and then plug it back into this equation, okay? So let's go ahead and get the first derivative, which is pretty straightforward. First derivative is going to be r plus n, which is this, times a sub n x to the power r plus n minus 1. And the second derivative is going to be nothing more than just taking the derivative of the y prime again. That's going to give you r plus n, which you already had, then the power of this, okay, sorry, it's actually the power of this, and it's going to be r plus n minus 1, then a sub n x to the power r plus n minus 1 is going to give you r plus n minus 2. So that's the second derivative. So my next step is going to be take this y prime and y double prime, okay, and plug it into the equation. If I do that, this is what I get. So x square times y double prime, this is y double prime, x times y prime plus x squared times y. And if I simplify it a little bit, this is what I get. Summation n is equal to 0 to infinity r plus n times r plus n minus 1 a sub n x to the power r plus n. So that's this term. And similarly, the second term becomes summation n is equal to 0 to infinity r plus n times a sub n x to the power r plus n. Please notice the following. In the first two summations, the power of x, which is just r plus n. So that's very important. So we can combine these two summations, right? However, the last summation, the power of x is not r plus n, but rather r plus n plus 2, okay? Now, our objective will be to have the x's same power on the left side. And we can convert the last summation to something where we will have x to the power r plus n, and we do so by shifting the indices. So what we do here is this. Every time you see n here in this summation, in the last one, you're going to replace it by n minus 2. Okay? If you do that, this is what is going to happen. So let me just write it down here. So this is a critical part where some people get confused. You have summation n is equal to 0 to infinity a sub n x to the power r plus n plus 2, right? So I am replacing in every place I see n by n minus 2. So I have an n here, so I'm going to put n minus 2 is equal to 0 to infinity. I have an n here, I'm going to put a sub n minus 2 x to the power r plus, I have an n here, I'm going to put n minus 2, then this plus 2, okay? So now if I simplify it, this is what's going to happen. Summation n, now this is the same as saying n starts from 2 to infinity, right? N minus 2 is equal to 0 is same as saying n is equal to 2. A sub n minus 2, this n minus 2, negative 2 and positive 2 are going to cancel out. That's going to give you x to the power r plus n. Now see, by doing this, we are going to change this exponent of x to r plus n by shifting the indices. Now, if I did that index shifting, this is what I get, which I showed you. So I combined the two left summations that have x to the power r plus n, and the last one, I shifted the indices, and then this is what I got. An important thing to note here is this. If you look at the left summation, it starts at n is equal to 0. if you look at the right summation, it starts at n is equal to 2. So what we are going to do, we are going to try to align these two summations so that it starts from n is equal to 2, both of them. So we can do that by just taking out the first two terms in the left summation. So that means we take out the n is equal to 0 and n is equal to 1. Then it will be aligned. We can go from n is equal to 2 to infinity, and this one will also be, right summation will also be n is equal to 2 to infinity. So when I plug in n is equal to 0 in this portion, I get r times r minus 1 plus r times a sub 0. N is equal to 0 is going to give you a sub 0. Okay, times x to the power r. Now, remember on the right hand side, you have 0. So that means all the coefficients of x to the power any power on the right hand side will have to be 0. However, that leads to the following assumption that this times this must be 0. But by assumption, a sub 0 cannot be equal to 0. So this cannot be 0. All right? This cannot be 0. If this cannot be 0, we are left with this term that has to be 0, which we find here. If we simplify it, we get r square is equal to 0 because negative and positive are going to cancel. That leads us to r is equal to 0. That's something we got by setting n equal to 0. And by the way, this equation is also known as indicial equation. So this is something you may want to keep in mind. Now let's go ahead and put n is equal to 1. If I plug in n is equal to 1 right here, this is what I'm going to get times a sub 1. And if I factor out r plus 1 from both of these, I'm going to be left with r plus 1. So r plus 1 times r plus 1 is r plus 1 whole square. So r plus 1 whole square times a sub 1 is equal to 0. But r plus 1 is not 0. 1 whole square is not 0. Why? Because we found r to be 0. So 0 plus 1 is 1. 1 whole square is just 1. So that just tells me a sub 1 is equal to 0. All right. Now we have the indices aligned. So look, the first summation starts at n is equal to 2. The second summation also starts at n is equal to 2. Now, these guys are going to have same exponents. So on the right hand side is 0. That means all the power, all the excess with any exponent will have coefficient 0. So if we compare the left and right, the coefficients on the left must be equal to the coefficients on the right. So the left side coefficient is this, which is just this up to a sub n right here. Okay. So that's just this first term, and the second term is just a sub n minus 2 plus a sub n minus 2 is equal to 0. Okay, now if I factor out r plus n, and I'll get r plus n minus 1, then plus 1 from here, that's going to give me r plus n. So r plus n times r plus n is r plus n whole square times a sub n plus a sub n minus 2 is equal to 0. This, by the way, is called recursive formula or recursive equation or recursion or recursive formula. All right. Now, if you solve for a sub n from this one, you will get a sub n is equal to negative a sub n minus 2 over r plus n whole square. And remember, all of this is going to be true for n greater than or equal to 2. Okay, for n is equal to 1 and 0, we have already isolated those terms. But we already found r is equal to 0 by setting n is equal to 0. So that means this r is gonna be going away. So that leaves me with a sub n is equal to negative a sub n minus 2 over n square for all n greater than or equal to 2. Now we are going to take the recursive formula, which is a sub n is equal to negative a sub n minus 2 over n square, and find the coefficients a sub n of our solution. One easy thing to do is look at a sub 1, which we found previously to be 0. Now that means a sub 3 is gonna be equal to negative a sub 1, because 3 minus 2 is 1, right? Divided by 3 square. But we found a sub 1 to be 0. That means it's gonna be just 0. Similarly, we will find a sub 5, a sub 7, a sub 9, all the odd subscripted coefficients to be 0. Okay, so this is equal to this is equal to is equal to 0. So that takes care of all the odd subscripted coefficients. Now that makes our life a little bit easier. We are going to consider only the even subscripted coefficients, that is n is equal to 2, 4, 6, 8, 10, etc. So if we put n is equal to 2, this is what we get. N is equal to 2 is going to be a sub 2 is equal to negative a sub 2 minus 2 is a sub 0 divided by 2 square. Very easy, we found it. Now for n is equal to 4 is going to be a sub 4. I'm using this recursion formula. Okay, is equal to negative a sub 2 over 4 square, which is the same as negative 1 over 4 square times a sub 2, which we just found right here. Okay, a sub 2 is negative a sub 0 over 2 square. So that's going to give me a sub 0 over 2 square times 4 square. Now let's go ahead and do the same thing for n is equal to 6. It's going to be negative a sub 4 over 6 square. So negative a sub 4 over 6 square, if I replace a sub 4, is going to give me a sub 0, and negative there of course, over 2 square, 4 square, 6 square. And for n is equal to 8 is going to be a sub 8 is equal to a sub 6 negative over 8 square. Again, I'm going to substitute a sub 6, the value that I got right here, and that's going to give me a sub 0 over 2 square, 4 square, 6 squares, and 8 square. Now, in general, if you're dealing with n, even n's is going to be 2k, right? K is 1, 2, 3, 4, etc. Is going to be a sub 2k is equal to negative 1 raised to the power k, because of the sign alternating between positive and negative. That's going to take care of that, times a sub 0 over 2 square, 4 square, 6 square, 8 square, up to 2k square. That is the same as saying negative 1 raised to the power k times a sub 0 over 2 times 4 times 6 times 8 times 10 times 2k whole square. Now I'm going to take this term 2 times 4 times 6 times 8 times 2k, right? All of it whole square. Now I could simplify it as follows. From the first term I will factor out 2, from the second term I will factor out 2, from the third term I will factor out 2, right? Etc. So that's gonna give me 2 to the power k, because there are k of them, right? Times 1 times 2 times 3 times 4 times up to k. Don't forget the square on the top, and then that's gonna be equal to 2 to the power k times 1 times 2 times 3 times 4 times up to k is gonna be just k factorial, all of it square. That is the same as 2 to the power, now I'm going to distribute this exponent, 2 to the power 2k times k factorial whole square. There you go. That's what it is. And that's exactly what you see in the denominator, and the numerator is as it is. So I just found the even coefficients, a general term for even coefficients. Okay, so a sub 2k. Now my assumption, remember, for this equation was that my solution is going to be of this format. Y of x is equal to summation n is equal to 0 to infinity a sub n x to the power n. Now remember, we isolated the first two terms, a sub 0 plus a sub 1 times x plus n starting from 2. So pay attention, the first two terms have been taken care of. So n is equal to 2 to infinity a sub n x to the power n. However, we found a sub 1 to be 0. Remember, a sub 1 was equal to 0. So this term is going to go away. If we take that term away, we are going to be left with a sub 0, this first one, plus summation n is equal to 2 to infinity a sub n x to the power n. But remember, our n's are jumping one step ahead, right? Only the even terms. So we are going to have n is equal to 2 to infinity negative 1 raised to the power n a sub 2k. I'm going to replace 2k with 2n, okay? So it's going to be a sub 0 over 2 to the power 2n times n factorial whole square times x to the power 2n. So please pay closer attention to the power of x, okay? X to the power 2n. It's not n. You had it n here. Why do we have it 2n? Because remember, odd n's, odd a sub n's, a sub n of this format, all of them are 0. So those terms are going to vanish. So we are going to have a solution with even power of x only. And we found the coefficients for even powers right here. So my general solution to this Bessel's function of order 0 is this. So this is what we found by doing all the calculations. So this turned out to be pretty nice actually, even though it's a lengthy video with all the things and all the derivatives and summations and whatnot, but it's not too bad. It's okay. However, there is another solution to this Bessel's equation which is kind of harder than this one. So I kind of decided not to put that one on here. So I just gave you the easier solution. And at first, guys, this may sound a little bit overwhelming, a lot of information and 3 pages long problem and everything. However, it's not too bad, okay? So don't get overwhelmed or don't be afraid or don't get frustrated and give up. But rather, follow the process. Just see it a couple of times. Watch the video a couple of times if needed. I think it will start to make sense. It don't look as intimidating as you may think. It's actually not hard, but rather a little lengthy. That's what it is. But first time when you see it, it seems very scary. Oh my God, such a long problem with all the symbols and everything, but it's not too bad, all right? So hopefully this helped you, and I hope that this discussion was helpful. Thank you very much.